I guess before I start, I wanted to mention I think Sanyam, you're here. Some of the there's been an initiative to ask Jeremy to make the course 2 online available to some of the people that weren't included in the first round of choices, where he was looking for participation in the forum, and we have a lot of people that participate on our meetup, and we were thinking that they should also be given a chance to take the second class live. Sanyam, do you have an update on that effort?
So Kai had been kind enough to ask Jeremy, and he's actually approved of that. So what I think we're going to do is Kai has created a channel where we'll post the links, and the interactions on there will be minimum. So for all the discussions, we'll keep using the current Fast.ai deep learning channel. And for those of us that are interested in taking on the part 2, they have been added to part 2 channel. If they haven't, they can either ping me or Kai. We'll add them to the channel and we'll share the links in that channel.
Yes. Yeah. So it's not some people asked if we can also ask Jeremy if he can put them on the forums, on the Fastai forums. I personally would not do that because, yeah, I mean, that's pretty much not fair to all the other peoples that could not, that were not selected. And also I think that it's a little bit too much to ask Jeremy that he should add everyone manually to the forums. So he was okay with sharing the video links. So if you want to have the video link for course 2 and participate in this study group, then Sanyam, Christian, or me will add you to the channel where we'll share those links. And one of us is going to post the link as soon as it's available.
It's made available.
Okay, so I guess I'm concerned that we are able to reach all of the people who are eligible for this, to participate. So, how are we going to reach them all? Like, how are they going to know that yes, now it's going to be okay for them to participate?
Well, I told Jeremy that I'm only going to add people who are regularly participating in this study group, and so if people want to participate, they will hear about that, and we will.
Okay, right. Just people that are on this study group will hear of it. Right?
Yeah.
Okay.
I mean, there are probably already some people who just wanted to have the link, and I think it's not. Yeah, it's okay, but there are around 65 people now in the group for the video link sharing. So let's see how big the study group for part 2 is going to be. Yeah, okay. But I told him that I'm just sharing the link with people who want to participate in this group, because the reason why I asked him was that I told him that this is a study group which is doing Fastai for almost a year now, and that it would be kind of sad to tear this group apart. And he agreed and said, sure, you can share the link. But I told him that I will only share the link with people that want to participate in this group regularly. So
great. Okay, so that's good.
Quick announcement. I shared a link in the chat. So apparently the polybot or the polling bot isn't working. So if you're interested in volunteering to do one of these presentations for the part 2 of our meetup, please make sure you add your name inside of the Google Sheet. And if you haven't been added to the channel and if you're interested in taking part, please tag Christian or Kai or myself and let us know that you want to be added to the channel.
Okay, any other announcements?
I think that's all from my side.
Okay, great. Okay, so chapter 6 is a large chapter. There are a lot of topics, and so I'm going to try to do some of them. I'm not going to be able to cover all of it. The Rossmann Stores competition, where he demonstrates how to use embeddings on categorical variables. I'll wrap that up. Then we'll talk about regularization, the different forms of regularization that we've learned about. I'm not going to talk about augmentation since Sanyam has given some excellent presentations on that on this meetup. So I grade that one out. I'm not going to talk about it today. We'll talk a little bit about CNNs and In my preparation, I wasn't able to get to GradCam, although I wanted to, but I just didn't quite finish. So I'm sorry that I have to leave that one unfinished. And then there's an ethics discussion at the end of the lesson, and I'm going to skip that too because I think it's more important to get through the technical things, and it's easy to listen to the ethics discussion, and we can maybe discuss a little bit about that at the end if people want to. And and I wanted to, and I wondered what's the. I'm sorry. Go ahead, Philip.
Yeah, I just wanted to say I agree with your scheduling.
Okay, and I wondered if who's going to do is there going to be a mini presentation after the lesson review? I didn't quite understand whether there would be one.
I'll try to cover two paper discussions today.
Okay, great. Sounds good. All right, well then let's get started. So here's the schedule, rough schedule. I'll try to wrap this up at 9:45. Then we'll have half an hour for the mini presentations. Then we'll have open mic for 15 minutes. And then just to remind you, next week, the last lesson, lesson 7, I think John is going to do that review. And then the following Saturday begins our course 2, and we'll review lesson 1. And I forget who's going to do that. That's on the schedule that Sonia mentioned. People have already signed up for that. Okay, so the Rossmann Stores competition is a CAG competition, and it involves 3,000 stores. Well, in 7 European countries, and we're given a time series of data for 1,115 stores in Germany. I can't remember what the timeline for that is. I think it's maybe 2 years, but I'm not remembering it. Maybe somebody remembers what the timeline was. And the goal is to predict the number of items sold in each store on each day over a subsequent 6-week period. Okay. So there's just a few things here. Jeremy introduces this little trick because he wants to calculate, he wants to use a metric as the metric. He wants to use essentially RMS fractional error. Instead of RMS error, root mean squared error, which, and this is the formula that we want basically. And you can see it's the average of the squared deviations, but they're really fractional deviations, right? Y minus y estimate divided by y. That's a fractional deviation, and we're summing the squares, and then we're taking the average, and then we're taking the square root. So that's what it says, root mean squared. And Jeremy calls this a root mean squared percent error. I think that's a typo. It should really be called root mean squared fractional error, but that's just a little quibble. But the trick that Jeremy introduces is that instead of having to implement this formula, we can just take the log of the target value and use that instead of the target value in the formula, and then we would effectively get root mean squared fractional error. And that's because the log of the difference between two logs is the same as the log of the ratio of two numbers. The difference between the logs of is the same as the log of the ratio. So basically, I'm saying log A minus log B is the same as log A over B, log of the quantity A over B. So the little trick is to, instead of using the y values, use the log instead, just substitute them. And that's what on the next slide, this is the actual command that he uses. And you can see here that he says, somewhere here, my eyes aren't picking it out, but there's something about the log. There it is. Oh, sorry, right at the bottom here. Log equals true. That means take the log of the y values instead of using the y values themselves. Okay, that's the little trick they use. Okay. The other thing that he mentions is when you run through this, he basically did a lot of the pre-processing in a previous notebook that was a part of the class Introduction to Machine Learning for Coders. So I've got a link to that notebook, and you actually have to run that notebook and get the pickle archive because it actually does the pre-processing and saves it a pickle archive. So that would be your starting point for this notebook that he in this lesson. You have to start with this. You have to get this. You have to build this pickle data archive using the notebook from the previous class. Let's see. The second interesting thing about this is he sort of shows the Fast.ai feature called Add Date Part, which is a really cool feature. It basically does automatic feature engineering on time series on time tags. So what it does is it takes the input, the date is the time tag column in the data frame, and what it does is it automatically generates new columns for all kinds of features that you can get from the time tag. Like you can, the time tag will be something like, August 23rd, 2001 at 10 o'clock GMT, something like that. That's what a time tag, that's the kind of information a time tag will have in it. And what this add date part does is it basically takes apart that time tag into a whole bunch of new features like year, month, week of the year, day of the month, day of the week, day of the year. And then it introduces Boolean variables, indicator variables for whether this day is the start of a new month or the start of a new quarter or the start of a new year. So there's a whole pile of, and then also there's another feature called elapsed time since 1970. So that's called the Julian date usually, and it's usually in seconds. No, I'm sorry. I'm not sure. It might be in years. I don't know what the units this will have, but the point is that you generate a whole bag full of new features out of the time tag, and it automatically adds columns for each of these features. So that's a really cool feature of Fast.ai. It's built into the Fast.ai library. Let's see. Then he talks about the pre-processing steps that you do. Pre-processing is basically a set of operations that you run once on the training set, and then with the metadata that's generated, you then share that with the validation and test sets. And I'll make that a little clearer as we go here. He talks about three different pre-processing steps for this pipeline, and excuse me, one of them is categorify, one of them is fill missing, which you can sort of imagine what that does, and the third one is normalize. We'll go into the details of these in a moment, but the point is that he's creating a pipeline called procs, and it's basically a list of these operations, and then he passes that to the when he creates the data bunch, the call to that process passes all of the pre-processing steps in by means of this list called procs. So here's let's see, tabular list procs. Somewhere here, there it is, procs. He passes in the list of pre-processing steps into the command that creates the data bunch. Okay, now what are these pre-processing steps? First of all, it's the first one we'll talk about is categorify, where he lists the set of unique values for each category. So like if you have I don't know, something called colors, and colors are red, blue, and green, then there are three unique values for the category of colors, and that's what would be here. So he lists the set of unique values for each category. Then he maps those values to integer numerical codes that are greater than or equal to 0, so natural numbers. And the reason for this is that he's preparing the data to go into the neural network. Neural networks need to deal with numbers. They can't deal with categories or things like that. There's a special code of a -1, a special numerical code -1 for a missing, if there's a missing value. So, for example, if you have the category called colors and you didn't get the color for this particular data point, then that would be a missing value, and it would be replaced with its numerical code would be -1. And then after that's all set up, Fast.ai adds 1 to each code so that the -1 becomes a 0, And now the codes can be used as lookup indices when you do the lookup in the embedding matrix. And then so there's this command dataframe.cat.codes with lists of the numerical codes that you have. And here, when we talk about passing the metadata, sharing the metadata with validation and test sets, the metadata that's generated by this step is the numerical codes. Okay, and what this means is that if you have a certain set of categories that you saw in the training data, then that set of categories is what you apply, is what you look for in the validation data. So on. All right, the next step is fill missing, and here for each continuous variable, it automatically creates a column which is that variable's name underscore NA, which is a Boolean indicator for missing values. So whenever that particular value is missing in a data point, then that column gets a 1, a Boolean indicator. And then if there is a real number there, then that column underscore NA gets a 0. So it's just a Boolean indicator. So it automatically creates this new column that keeps track of missing values. And then it fills the missing values with the median. If it's a continuous variable, it fills in that missing value with the median value of that particular column. And so for this step, the metadata is those medians that it uses to fill for each category. And so in other words, when you go to the validation set and you have a missing value, you don't fill it with the median of the validation of that variable over the validation set. You fill it with the median of that variable which you already had from the training set. Okay. And then the third step here is normalize. And then for each continuous variable, you basically subtract the mean and divide by the standard deviation, which gives you like a z-score. And for that step, the means and the standard deviations are the metadata. So again, when you're dealing with the validation set and you want to normalize, you subtract the mean and divide by the standard deviation, but the mean that you use is the mean of that variable in the training set, not in the validation set. And the standard deviation that you use is the standard deviation of that variable from the training set, not the validation set. Okay, so for this step, the means and standard deviations are the metadata that gets passed to the validation set and the test set later on. Are there any questions up to this point?
No, chat is clear.
Okay, fine.
I have a question concerning the imputation strategy. You mentioned that the median is imputed. Why don't they sort of get a measure of the distribution and then use the distribution or sample from that distribution to impute the data?
That's a really excellent idea, and I think that's a more sophisticated way to do it. And I think this is just sort of the first cut way to do it. I'm not sure if Fast.ai has built in a way to do what you're suggesting, but that is a more sophisticated way to do it. It's more Bayesian, and I would actually prefer that. I don't know if you can actually select that method in these Fast.ai commands, or if you have to write that for yourself. But yeah. But that would be a good exercise if they don't have that choice within the Fast.ai library. Then one could write a little class that would perform that. That's a really good idea. Other questions? Okay. Okay. So next, I wanted to go over this. People seem to be and I too have been very confused by when I look at these diagrams that Jeremy draws with the weight matrices and the activations and so on, and his brain seems to think of matrix multiplication in a way that I couldn't figure out. So I looked at this really carefully, And I've now understood that this is actually a superior way to do things. And in other words, there's method in the madness. So let's look at this, one of these typical Jeremy drawings that he makes. I've isolated this piece in the middle here, which is kind of like one, it's basically a whole series of steps that are just like this one. So you start with an activation, a column of activations, that's your activation vector. And then you apply to it a weight matrix, which basically you want to multiply the weight matrix times the activation vector. And then you end up with another set of, with the next set of activations in the chain. So the way things work in neural networks is everything flows from left to right. You're starting with the input data, which kind of acts like an activation, and then you act on it with the first linear layer to produce the activations, and then the cyan is basically like the raw activations, and the purple is the raw activations that are then acted upon by the nonlinear layer, which is the ReLU in most cases that we're doing, right? So going from cyan to purple is basically applying element by element the ReLU function, okay? So that's our starting point, and that's the notation we're talking about. So, so the purple, again, is the activations after applying the ReLU, okay? And in this case, for this middle layer here, it's a 5x1 vector, column vector. The yellow is a weights matrix. In this case, it's a 5x8 matrix. And the output activation, which is the raw activation, is an 8x1 vector, right? And I noticed that I made a mistake here. That's 8x1, okay. So normally we're trained to think of matrices multiplying column vectors from the left. And that's why this is so confusing, at least it was to me. So what you really want to do is you want to take the transpose of this weight matrix and multiply it by that column vector, and that's what will give you the cyan column vector, right? And so I have it written down here, W transpose matrix multiply times A gives B. And you could check that it works. W transpose is 8x5, right? And we multiply 8x5 by 5x1 column, you get an 8x1 column. So that all works, that all checks out. So the first thing I realized then is that this notation of Jeremy's really means W transpose multiplied from the left on A, even though it's kind of reversed here. So then I was asking myself, why does Jeremy write it this way? And I realized that because in neural networks everything flows from left to right, it's more natural to think of in some way as A times W equals B. And Jeremy is thinking that way. And he's got a new sort of a definition of matrix multiplication in which the ith element of B, you form this matrix B element by element. The ith element of B is the dot product of A with the ith column of W. So the first element of B here is basically this column dotted with that column, the first column of W. The second element of B is this vector A dotted with the second column of W, and so on and so on. The last element down here is this vector A dotted with the very last column of W. Does that all make sense? So that's kind of a really simple way of thinking about matrix multiplication from sort of in a reverse order like Jeremy is. So you can just think A times W equals B. And that's how Jeremy is thinking. I think I've decoded the way he's thinking about it. And I think it's really a genius way to think of it. It's much more natural in my mind than it's kind of like matrix multiplication adapted for neural networks because we want the processing to flow from left to right. Are there any questions up to here?
I know that we had a pretty detailed discussion on this and looked into this on the first time we did the Fast.ai course, the previous version of the library. Maybe I can find the part of the video and then post it. That Someone, I think, I don't know if I even did it myself, but someone held a mini presentation on that, and also on how this matrix multiplication works with embeddings. So maybe I can find that.
That'll be great.
Yeah. So anyway, this kind of helped me to think about, so that I can now look at these diagrams that I see in Jeremy's talks, and I can understand what he's doing. Okay, so the next part of this presentation is we're going to talk about regularization. And in this lesson 6, Jeremy introduces 4 methods of regulation. Regularization. Some of them are reviews but I basically gathered them all here together so we can talk about them all in one place. The only one that I won't talk about is data augmentation. Again, since Sanyam has done such a terrific job in the last couple of mini presentations of showing his work in that area. Okay, so the conventional wisdom when you approach machine learning, and this is drummed into me from the very first machine learning course I had, is avoid building complex models, because then you're going to have a problem with overfitting. But Jeremy throws that out the window, and his reply is, and this is just a paraphrase, nonsense. Go ahead and build as complex a model as your compute resources can comfortably handle, and then don't worry, you can control overfitting by applying various regularization methods. And that was just one of the surprising things that I've heard out of Jeremy's mouth, one of the many surprising things I've heard out of his mouth, and it's really sort of in my mind, it sets up a new paradigm. Try to make, don't be afraid of complex models as long as you can regularize them afterwards, and control the regularization so that tune the regularization so that you can control the overfitting. Okay, and so there's the methods that we use are okay, and what do we mean by, everyone probably knows this already, but let me just go through this. Regularization methods are basically techniques that mess around with the model fitting process, and it making it more noisy. They either make the model more noisy, or they make the data more noisy. In the case of data augmentation, you're basically adding noise to the data. Why do we do this? And the idea is to prevent the model from overfitting. What is overfitting? Overfitting is the tendency of a model to learn to memorize the training labels, so that it's basically able to predict correctly as long as you give it the training labels. But then when you try to give it a new data set, it doesn't know what to do. It doesn't do a good job because it's only really understanding what to do with data that's like the training data. Okay, so the goal is to build a model that generalizes, that doesn't overfit and performs well on new data that's outside of the training set. So now let's talk in a little more detail. Dropout regularization, the best way to introduce that is just by a picture. It's really worth 1,000 words. So here's a normal standard fully connected neural network. And here's what happens when you apply dropout. At each level, a level is like a horizontal set of nodes here. You're drawing a probability that at each node you're drawing a number that tells you whether you should or shouldn't drop that node. So you draw with a probability. So for example, if you set P1 meaning the probability that you use at the first level, if you set P1 equals to 1/2, then at every node you flip a coin and decide whether you're going to drop heads you drop the node and tails you keep it, something like that. The probability doesn't have to be 0.5, it can be anything. And at the next level, you can have you could use the same probability, or you could use a different probability that's only used on level 2 for and then you apply that coin flipping process to every node on level 2, and you decide whether you're going to keep it or drop it. Now dropping the node simply means setting the activation to equal 0. That's all it is. The weight, you don't change the weights matrix, you just set the activation equal to 0, so that those particular weights that hit that activation don't figure into the model. And then on the third level, the same thing. So the prescription is that for each mini batch at each level J, you randomly drop activations, i.e. set them to 0, with a probability Pj at each node. And then Jeremy introduces this trick that Fast.ai does. You scale the remaining activations at each level. You scale them by 1 over P so that the sum of the activations at that level will remain roughly constant. It would have been, it will be the same. The sum of the activations will be the same as it would have been if you hadn't dropped anything. And I think that's just for, I'm not sure why that is needed. It's probably for stability of the model. And then the other key thing is you apply dropout during training, not during test. So what dropout regularization does is it adds noise to the model, because for each mini batch, a different perturbed version of the model is generating the weight updates, right? For each mini batch. So for example, in this picture, this is a different model than this is, right? This is the fully connected neural network. This one with dropout applied is not the same model. It's a slightly different model. And that model is going to be used to do the weight update for that mini batch. The next mini batch, you're going to draw a different looking network, and then that new network, that new perturbed version of the original network, is going to be used to generate the weights. So you can think of this as sort of the weight updates. Every weight update is done by a noisy version of the model, and that's what helps to get the regularizing effect, because no one node is allowed to dominate. No one node or group of nodes is allowed to dominate, because every time the model is perturbed, and those nodes that might have dominated are eliminated out of the version of the model that gets used.
Okay. Can I quickly jump in
Sure.
on that question on, they said, you don't know why the 1 over P exists. So,
Yeah.
So let's take a simple use case. Okay, there are only 2 nodes in the model. Okay, and it's just you and me. Okay, and then we are both, like, you can think of it as we are 2 different models. Okay, 2 different like neural network nodes. Okay, and then information comes in, and then we are learning something about the model, and we're going to give an answer, and then let's say the output is going to be the average of those two values. Okay, the next level node. And then we want to say, no, I don't know. Let me do a dropout, and I'm only going to give information to one of the person at any one time. Okay, so it's sometimes you get the information, and then I'm turned off. Like the information whatever I generate is ignored, and then so it needs to be whatever. So in the normal state where both of us are giving information, our output is averaged. Okay, so it's going to take the divide by 2. Okay, but when only one of us is giving the information, you might actually have whatever output you generate may need to be scaled by 2. Okay, scaled by number of dropout nodes. So this 1 over P is purely for scaling purposes, because otherwise the output that gets generated will basically be will not be the same average value. It will be scaled up or scale, if certain only some nodes give information, and scale down if all nodes give information. So that's all this 1 over P is really doing. And so just to make sure that whatever we are learning as the output, we are not trying to compensate for the other person not being there. It should, so that's why it applies the ratio on it. This is just how dropout works. So it is not something Fast.ai does. It is just the process of dropout.
Right. I think, but I guess the point is that Fast.ai does it automatically for you. You don't have to think about it. It does that. And I like the way.
True. But all networks do it that way. So whether you use TensorFlow, Keras, PyTorch, they all do it automatically.
Oh, okay.
Yeah.
But yeah, so that's a part of the dropout prescription. You can't leave that step out. I guess that's the point. But I like the way you're thinking about it, because I thought of it as the reason why you're doing it or why you're scaling it is so that the sum of the activations would be the same. But what you said makes me think that it's the average that's and it's the same thing. It's the same thing really. It's the average activation is staying the same after if you apply that scaling factor. The average activation that guarantees that the average activation stays the same. So yeah.
Is this applicable for even if the dropouts are not done on the inputs?
The dropouts can be done on the, and I think that in Fast.ai he allows the dropouts to be done on the inputs. The inputs can be treated as just another set of activations.
They are done on the input, because when the first node is switched off, then it's the same thing as if the input would not be given to the network, right?
Yeah, yeah, and this is very reminiscent of bagging. It's called bootstrap aggregation in the random forest, where now you're constructing trees and you're leaving out some of the data when you construct the trees by this process of bootstrap aggregation. What you're doing is you're choosing your inputs. You're choosing a bootstrap sample of the inputs, which means if you have n inputs, you choose from that set of n, but you sample from the inputs with replacement. So every time you pick one of the inputs, you then put it back and then choose again, and then you put it back and you choose again. So what you end up with is a set of n inputs, but those n inputs have duplicates, because some of the times you'll choose the same one that you already have. And so what that means is that a bootstrap sample is an incomplete. It doesn't include all the samples, and that's similar to this dropout strategy, which doesn't include all the nodes, or as Kai just mentioned, it doesn't include all the inputs. At each mini batch, you'll be leaving out some of the inputs because they will have been dropped out. So that's a very similar. It's a very similar strategy. And then at the end, you average all of these bootstrap sample. You build all these trees. Let's say there are m. You build m trees out of these bootstrap samples, and then you average them all. You use them to predict, and then you average all the predictions together. So that's another way of preventing any particular data point or set of data points from dominating the answer and dominating the prediction.
Hey, can I just offer real quick? Can you hear me?
Yeah.
I just wanted to share that I recently published a paper on Medium about a theory for the mechanism behind Dropout, which I posted in the comments. It's called Dropping Out for Fun and Profit. And you guys are, any retweets are welcome. And I hope you guys might enjoy it.
Okay, great. Thank you, Nicholas. We'll have a look at that. Okay, so any other questions about Dropout? And then another takeaway, don't forget, is you only apply Dropout during training, not during testing. So during training, you apply Dropout and you build this model that is robust to it's robust to overfitting. Now that you've got this model, you want to apply it to all the data in the testing set. So you don't drop out thing. You don't do the dropout process when you're applying the model to the test set. You've already built the model using Dropout, and now that model is the best model you can build, and you just apply it straight to the test set without dropping anything. Does that make sense? Okay. There's no reason to apply Dropout during the testing phase. Okay. Okay, and then the second regularization method is weight decay. Weight decay is derived from L2 regularization. It's not quite the same thing, but let's look at what L2 regularization is for a moment here. So this notation is slightly different, but it's not too recognized. It's not unrecognizably so. The h sub theta is the estimate for y. So it's y. It's basically playing the same role as y hat. The thetas are the weights, and the lambda is the L2 regularization parameter. And then so here's the sum of the weights. So basically, you're taking this mean squared error, this sum of the squared error loss function, and you're adding to it a constant times the sum of the squares of the weights. So what does that mean? When you try to minimize the loss function, you're trying to minimize two things at the same time. One is you're trying to minimize the sum of the squares of the errors, but you're also trying to do that with the constraint that you're also minimizing the sum of the squares of the weights. So what that does is it forces the weights to be small. It constrains the weights to be small. And depending on how much you've cranked up this lambda parameter, you can have a larger or a smaller effect on that. You know, if you set lambda equals 0, then you're back to the normal mean squared error loss, or squared error, sum of the squared error loss. And if depending as you tune lambda as the hyperparameter, the more lambda you put in there, the more you're emphasizing that you want the weights to be small. So constraining the weights to be small reduces the flexibility of the model to fit the data, and that in that way it prevents overfitting. So again, here you're perturbing the model, basically making the model more noisy. Weight decay regularization is a way to add noise to the model, and along with this general theme of what regularization does. It's usually adding noise to the model or noise to the data. Okay, so what's weight decay? Well, weight decay is just a slightly different way of looking at L2 regularization. Instead of changing the loss function, you basically add the extra term from the derivative to the weight update rule. You can see that derivative of this term is going to be lambda times, it's going to be 2 lambda times w. So you end up subtracting the new weight is the old weight plus the adjustment due to the loss function, and then you subtract minus 2 lambda times the weight from it, and that's the extra term from this derivative. So instead of changing the loss function, you basically change the weight update, and it accomplishes the same thing as L2 regularization. And Fastai uses weight decay instead of L2 regularization. That's just the way they've implemented it. All right. Any questions about weight decay regularization? Okay. Okay, and then the fourth method the third method is, of course, augmentation, which we're not going to discuss. The fourth method of regularization that Jeremy brings up in this lesson is batch norm. Batch norm is, strictly speaking, is not just regularization. It does other stuff for you, but in this case, let's just go through what it is. So first you calculate for each mini batch, you calculate the mean, and that's this mu sub b. B is for batch. Then you calculate the variance, and that's here. It's basically the sum of the squared deviation, the average of the sum of the squared deviations, using this mean that you calculated in line 1. And then the next step is you normalize, subtract the mean, divide by the standard deviation, and in this case they added this epsilon here in the denominator, and that epsilon is just a constant. In Fast.ai they default it to 1 times 10 to the minus 5, and I think what it does, it's for numerical stability, really, when you calculate these things. Okay, because what happens if you have a very small number down in the denominator, then things start to go crazy, so you stabilize it with this extra little term, epsilon. So epsilon is just a constant, right? And then finally, this is the important step. It's basically a scale and shift step. You multiply the normalized data by gamma, by a factor of gamma, and you add to it another factor beta. So this is scaling. The gamma is a scaling parameter, and the beta is a shifting parameter, and that's what this batch normalization is all about. The couple things to note: the actual mean and standard deviation used are not straight mean and straight standard deviation. They are exponentially averaged weight, mean and standard deviation. And remember, exponential averaging is when you is a way of updating is a way of taking into account, giving more weight to the recent values of the mean than to the values from many mini batches before. So it sort of keeps a little bit of the history, and it keeps the values of the mean and standard deviation a little bit more stable. They're not going to jump around as much when you use exponentially weighted averaging. And okay, so that's the mean and standard deviation that you use is the exponentially weighted ones. And then finally, the beta and the gamma, these scale and shift and scale parameters are learned. They're not just constants; they're parameters that are learned by the model. And what that does is it gives the model more flexibility to improve the match to the data. Jeremy was giving an example where you want to generate categories from 1 to 5. You want to be able to fit a model and classify things between 1 and 5. But when you first apply your model, you find that, oh, all of my categories are only between 1 and 1.5. So I've got a really poor match. So that's what this scale and shift allows you to say, okay, so stretch out that 1 to 5 and shift it, and then you can match the scale that you're after, which is, sorry, stretch out that 1 to 1.5 range and then shift it, and then you can match the 1 to 5 range that you're looking for. So it gives the model a little more flexibility. And so you would think that, well, that's not going to help you against overfitting. That's going to make it worse. But the actual benefit of the batch norm for regularization is this use of the exponentially weighted mean and standard deviation. That's where the regularization effect comes in, because it doesn't let the mean and standard deviation jump around from batch to batch. It keeps them more smooth. Okay. So batch norm is used for continuous variables, and part of its benefit, and this doesn't have anything to do with regularization, it's been found that it reduces the variance of the loss surface. So instead of having a really jumpy, wiggly loss surface, it's more smooth. And this means that you can use a higher learning rate and train faster. So batch norm is sort of a magic bullet here, and Jeremy says you always want to use it. Okay, he also, he goes through some discussion about how in the beginning batch norm people didn't really understand why it worked. They even published papers positing, with their theories of why it worked, and then they found out they were all wrong, and that really the reason why it works is more related to the fact that it reduces the variance of the loss surface, makes it smoother. That's why it works well. All right. So that's where most of my preparation has been spent, and I think I've gone over time. I'm going to have to leave this part out. I didn't do much on it anyway. I just presented what it's a nice visual presentation of what a convolution is. It's basically a kernel with numbers in it that are selected specially to do some function that you want it to do, like maybe a vertical edge detection or horizontal edge detection. And you apply that kernel to an image, and then what happens is you get a new version of the image which has changed dimensions, and it reflects the contributions of this, the operation of this kernel. So, for example, here, applying this kernel to the first upper quadrant of the image, you're basically just summing the product element by element of alpha times A, beta times B, gamma times B, delta times E. You're summing those together to get the new pixel value, and then the same thing. Next you move this convolution kernel. You sort of do a raster scan. You move it. You start, and then you move one step to the right. You do the same operation, the summing operation, and then you get the new value here. Next, you move the raster scan to here, and you multiply element by element with the convolution kernel, and you come up with the sum, which is this R, and so on. That's the way. And now there are a few other concepts about padding, where you add an extra layer of zeros around the edges, so that you will get a smooth transition to the edge of from the edge of the image instead of an abrupt transition. You can imagine that if you try to apply this to a 2x2 image, you only get one value. But by padding the 2x2 image with extra pixels, you can then get more than one value out of it. The other concept, which I won't go in here, is stride, which means instead of doing a raster scan element by element, you skip. You skip. So that would apply to a bigger frame here. You apply to the first quadrant, then you skip over one element and apply it next, and you skip. Or you can skip 2 elements, or you could skip 2 pixels, or you can skip 3 pixels. That would be the stride number. Okay, that's all I got. I'm going to turn it over to Sanyam for the next part of the meeting. Thank you all.
I'll just wait a bit if there are any questions from your presentation, if anyone wants to ask that.
Yeah, I have a question, and the question is, you mentioned the L2 regularization. There is also another regularization possible called L1 regularization, where instead of the squared weights, you take the absolute value of the weights, and I was wondering why that is not used in this case.
Actually, you can use it. I think Fast.ai allows you to choose, and I think there are even more ways to do it than this. But yeah, L1 regularization has a different effect. It also mitigates towards small weights, but it turns out because of the way it works, it helps you to eliminate weights. Like it drives some of the weights to 0. So it's kind of a way of dimensionality reduction. It actually allows you to do, it's kind of built-in form of dimensionality reduction. Because if you apply L1, it turns out that some of the weights become 0. And when a weight becomes 0, that's effectively throwing away, making the model smaller. So yeah, L1 regularization. So what people do in practice is they get a feeling for whether they want to use L1 or L2. And then they try both, and then whichever one works best, they pick it, right? And there's another one called Elasticsearch, where you do some kind of a linear combination of L1 and L2, so you get the benefits of both of them.
Yeah, I think one of the reasons the L1 is not used in neural networks is, let's say you identify nodes 1, 3, and 5 are not useful. Are you going to prune them and remove them from your network? Most likely not, right? You're going to leave them in there. So there's no benefit of actually, setting some of them to 0 in your final network. It's only useful if you're trying to, if you have a tabular data of 500 inputs and you are trying to identify which ones you're trying to do dimensionality reduction, as I just said, so that you can make it a simpler network. But if you're not going to generate a simpler network, you're not getting any benefits of L1. L1s are useful if you're trying to compress the network, like you're trying to prune the network, and so that you want to fit to a smaller GPU or something like that, then L1s can be useful. But that's why in general you don't see L1s. And also L1 loss curve has this V shape where gradients can be undefined at that point. So L2 has a squared norm, so it's easier to compute the gradients. So that's one of the reasons why L2 is preferred over L1, and also you're not getting benefits, you're not taking advantage of benefits of L1 if you are not pruning the network, which you most likely are not. So that's another reason you don't use L1.
Okay, that's great insight. Thank you. Any other questions? Okay, we'll turn over to Sanya.
All right. A few more things that I want to sort of point out is Kaggle kernels now use P100 GPU. And I think that's the P2 instance that you get in AWS. So that's something worth checking out. The last 2 lectures of...
What's a P100 GPU? I mean, is it equivalent to a 1080i, or what is it?
I'm not sure how the comparison is, but it's better than the K80 that they originally supported.
What's a K80? I don't know what these terminology.
K80 was the original GPU that the Kaggle kernels or Google Colab supported. I'm not sure what Google Colab uses right now, but kernels now support or use P100. Okay,
great. That's great to know. Yeah, because I know when I use Paperspace, I get a P100. So yeah. So that's pretty good.
I mean, it'll be faster for sure. So you definitely want to give it a shot. Maybe it's now less annoying to use kernels.
What's the most annoying thing about using Kaggle kernels is that you have to execute the whole damn kernel before you can save it. That's why for me that's a game. That's the showstopper. But
I think the issue with Fastai is it's sort of CPU hungry on the kernel, so you get these errors here and there, which is why it's not a good place to run those commits. And another thing is that the last 2 lectures of Fastai will be using Swift for TensorFlow. So if you're familiar with Swift, we'll be glad if you could do a mini presentation on that. And can everyone see my screen okay?
Yes, we can see it.
So the paper that I had discussed during the last meetup, I've sort of proposed a project on the forums. So if you're interested in doing these NLP data augmentation experiments, please feel free to ping me on there. So what I'm going to do is I had earlier committed to sharing 1 machine learning hero interview each week. And now I'm trying to commit to sharing 1 paper, 1 5-minute paper discussion each week in the form of blog post. So this is sort of the first in that. I'll actually discuss 2 papers. So in this paper, the authors have compared their approach to ULM fit, which is Jeremy's approach of doing transfer learning on NLP. To give you a bit of context, what this does is you have a pre-trained model on Wikipedia on the Wikipedia dataset, which is Wiki text 103. You use the language model trained on this. You fine tune it to your target dataset. The target dataset being, for example, IMDb sentiment dataset, and finally you tune it towards a target task, which would be in this case sentiment analysis. So in this paper, the authors have proposed another, which they approach which they call embarrassingly simpler compared to these standard approaches. They try to address 3 issues, which are the other approaches around this pre-training and transfer tuning is computationally expensive. They call the learn.fit1 cycle approach to be sophisticated compared to this. And a common issue with RNNs is it has something called catastrophic forgetting. So these are addressed in their approach. Now, if I could point your attention towards this diagram, the most important, in my opinion, variation that they do to LSTMs is, let me zoom out a bit. So they add these 2 loss layers towards the end of the model. So what happens is you have your original language model loss and you have your auxiliary loss. So what happens, you pre-train your model, and when you're doing this target task approach, you have 2 loss values coming in. That's a little tweak they do. So you take your pre-trained language model, which the authors train on Twitter and Wikipedia. Then you create these sort of tag towards the end where you sum up the loss from the task, which is your auxiliary loss, as well as your language model. Now, as you might expect, during the initial epochs, the language model would be this sort of guide for this approach. So you'd like to give more weightage to your language model. This is decided by gamma, which I had to use Y for here. Please excuse that. You sum these up, and you might expect that towards the later epochs, your target task will be more trained, so your target layers will be better trained. Then you'd want to decay this gamma parameter to give more weightage to the task loss, whatever task you're trying to aim at. And another approach that they share is sequential unfreezing. So all of these are little tweaks they do to make transfer learning better. What happens in sequential unfreezing is similar to what we do for resonates in Fastai. So initially, for a set number of epochs, you unfreeze your final layers. You train those to a bit. When you're happy with the accuracy, you'll unfreeze another bunch of layers towards the outer layers. You will train those. And once you're satisfied with that and you want to push the state-of-the-art accuracy using this model, you'll unfreeze the complete RNN model or LSTM model, and you'll train it throughout. That's sequential unfreezing. And they use two optimizers, so SGD for the, I think, language model, and ADAM for the target task. Just another little detail. To compare their approach with ULMFit, as you can notice, their model is called Seattle. So this generally performs better than ULMFit. Note that it is not the state of the art in all of these 5 standard data sets. These are sort of standard data sets in NLP. But it performs better than ULMFit and some of the other approaches around this comparison. Specifically, this is the comparison against F1 score and number of training examples. So F1 score higher, the higher your F1 score, the better your accuracy. And Circle, if I remember, yeah, Circle denotes their model compared to Plus, which denotes ULMFit. So specifically towards a smaller number of training data examples, you can see that the accuracy is better and the model performs better. Even towards a larger number of examples, it's slightly better than ULMFit. So these are the results that the authors claim. I think some of these approaches are sort of intuitive, specifically sequential unfreezing and decaying the weightage to the loss, specifically taking in two loss values. I'd be interested in, like, I've already proposed this on the forums if anyone is interested. I'd like to combine this technique and the EDA paper that I had presented last week, maybe as an experiment to check how does that perform on the IMDb dataset from the lesson. So any questions from this paper so far?
So as I understand it, sorry, go ahead.
This is Marcello. I have a question, Simon.
Please go ahead.
Yeah, I'm not very familiar with the subject, but I don't see if the article is speaking of something similar to what we have seen in lesson 3 on Fast.ai and the pre-trained language model we used in the IMDb, or it's something different.
It's the same. So the lesson introduces this approach called pre-training and then fine-tuning towards your task in NLP, which is the standard in image classification at least. So in this paper, this is a 5-minute discussion article on the paper, and the authors have shared simpler techniques for doing what the lesson has taught us. So they claim better results on this task that the lesson has taught us.
Okay, understood. Thanks.
Joseph, you had a question?
So you mentioned that you ended up completely retraining the language model that you used, that you started with, right? And that's why you said that the drawback of this method is that it just takes a long time, and that's because you have to complete. I presume that's because you have to completely retrain the language model.
I think this is faster compared to ULMFit, so that's what the authors have claimed.
Oh, okay.
The approach is you sequentially unfreeze your model. So layer by layer, you unfreeze your model, and towards the end, towards the end, you train the complete model for maybe 1 epoch or 2, and you might. So the source code isn't available yet. The authors have promised that they will share it later. So maybe they like Fastai, they might use differential learning rates as well. If they do not, I think that's a good opportunity to experiment and see if we can improve their approach further.
Yeah.
Do you have an idea, Sam? Sorry, go ahead.
Yeah, could you say a few words about the two things at the top, the auxiliary LM loss and the linear layer that you've added to that they've added the model?
So originally, what I know happens here is you just have one loss value, right? Which is whatever target task you're trying to solve. Or the authors have claimed that if you add another auxiliary language model loss, which was the original language model, right? So you had this language model that we sort of fine-tuning. You accumulate both of these and account for both of these together, and that sort of gives you better performance on whatever task you're trying to solve.
So your loss function is essentially the sum of two things. The sum of the loss function derived from the original model plus this extra layer.
Yes.
I see. Okay.
And why, or actually it's gamma. Gamma is how much weightage you'd like to give to the pre-trained language model.
Yes. So what is the extra model? The second, okay, so I understand that on the top of that diagram that you just showed, on the left side is basically the old thing that we would have used, the the original loss from the pre-trained language model. But then on the right, there's this new thing, which is another it's another linear layer on top of the result.
So the datasets are classification datasets. So I sort of think of this as adding a custom head similar to what we do for ResNets, right? Fast.ai in the ImageNet model, you have your language model, you add this custom head, so to speak, towards your target data task while retaining the original loss layer as well.
Oh, okay. I think this is the idea of the catastrophic forgetting. This is the mechanism they implemented in order to mitigate against the catastrophic forgetting. In other words, the new layer, you're going to use the new layer, the one on the right, to learn, but you want to retain what you've already learned from the original pre-trained network, and that's the wet layer on the left.
That's exactly right. So to give others more context, catastrophic forgetting is overfitting in NLP. So you forget your original language model and you start overfitting towards your target data set.
Yeah. Yes, good.
Can I move on to the next paper or any other questions? All right, so called Bag of Tricks for Image Classification with CNNs. This is an older paper relatively, and it's sort of already pretty famous. From what I know, some of these tricks have already been applied to inside of Fastai. I'll quickly go over these few tricks. I think there are 5 or 6 of them. The first one is called linear scaling of learning rate. So when you're setting your learning rate for your batches in SGT, the authors have suggested that as you increase your batch size, as we know that SGT picks out the batches at random, right? It selects the batch at random and you train over that, you adjust your loss values. So as we increase the batch sizes, you can expect that the variance from batch to batch will be lesser. So that allows us to set the learning rate more aggressively to larger values. So they've given us a formula. There are extensive studies inside of the paper of how much these techniques are helpful or hurtful. I skipped those for this discussion. But in general, you'd want to, they've set the learning rate using this formula, which is 0.1 into batch size divided by 256. Why 256? Because 256 is sort of the standard value where they would start. Another thing is called learning rate warmer. So let's say you're training from scratch instead of using a pre-trained model, right? Now, initially, your weights are untrained, even though you might have initialized them using some algorithm, but those are sort of untrained. So initially, you wouldn't want to set the learning rate as aggressively towards the later cycles. So how the learning rate warm-up technique works is initially you start with 0 and increase your learning rate right up to whatever value you actually pass to the model. This is set using this formula, which is current epoch multiplied by learning rate divided by number of initial epochs. So this again is another hyperparameter. Number of initial epochs is what we decide to implement the learning rate warm-up to. So let's say we're training for 100 epochs, and till 30th epoch, I'd like to warm up the learning rate, which is slowly increase it. There is some discussion in the paper of what values might be useful or might not. I've skipped those again here. Another thing, Joseph had talked about batch normalization. So there's this scale and shift that happens inside of, I think, batch normalization. So when you're doing this y into input plus bias, you initialize y to 0. And similarly, when you're doing regularization, so there's something called weight decay, which is a regularization technique applied to CNNs, you do not decay the biases. That's another technique that they've explained. Furthermore, the recent graphic cards support something called FP16 or mixed precision training. That's another thing that the authors have suggested that we should employ. So the initial issue with this was that FP16 is quote unquote go out of what you want or your network wouldn't converge. There have been some fixes that have been suggested to these, which is called mixed precision training, rather than just using half precision, which would be FP16. Few techniques that they've used is they've tweaked the model inside of the resonets of the model. They've changed the strides, which are sort of, again, a deep dive into connets. So they've claimed that if you set the stride to different values compared to what it is originally inside of resonets, you can expect a performance boost while not hurting the accuracy. That's another something you might want to look into if you're experimenting with ResNet 50 or similar. And like we as Fastai students are familiar with learn.fit1 cycle, but the authors have suggested cosine learning rate, which is sort of scheduled using the cosine graph that exists. And finally, there's this thing called knowledge distillation. So you have two models that sort of guide your training process. You have your teacher model and you have your student model. So knowledge is distilled from your teacher model to your student model. How does this work is you have a trained ResNet 151, for example, and the loss of those on compared to a ResNet 50 that you're trying to train are compared, and that guides your initial training process. I think this is again another interesting approach, knowledge distillation to apply to your ResNets. To talk about the results, again to give you some context, ResNext came out after ResNet 50. So after applying all of these techniques, and as you not as computer intensive as ResNext or equally as computer intensive, while performing better than ResNext and even SC ResNext and DenseNet, which are the papers that came after ResNet 50 or the models that came after ResNet 50. So if you apply all of these techniques to just image classification using the hyperparameters and all that, the authors, you can expect quite some pronounced boost. And on other tasks such as semantic segmentation, I'm not familiar with these data sets, but what the authors have claimed is, again, you would notice some boost on using transfer learning on these techniques. So I think this is one of the interesting papers where the authors, like, this is the motivation behind the paper as well, where they try to discuss these bag of tricks that sort of usually go unpublished or aren't shared heavily when you're claiming some state-of-the-art accuracy in a task. So this complete paper was a deep dive into all of these techniques and a thorough study of how much is each idea useful or hurtful. And I personally would like to read more papers along these lines if some authors decide to continue publishing more bags of tricks. I'm open to any questions from this paper discussion.
Someone just shared a link to the archive of the actual paper, but it looks like this is a summary published on Medium. Do you mind just sharing a link in the comments?
Sure, I'll do that. So I've started the series where I'll sort of summarize these papers and let you decide if you want to read the complete paper.
Cool.
Any other questions?
Okay, another excellent mini presentation by Sanyam. Thank you so much. Shall we devote, and not only that, Sanyam, you actually ended a minute early. That was great. So we have the next 15 minutes or so for a discussion or another mini presentation if anyone has something else to present. So
I can.
open mic, yeah.
I can present some work I've been doing on using the CAM heat maps techniques for my work.
Oh, great. We'd like to see that.
So yeah, I'll share my screen. Is it visible?
Yes.
Yeah. So basically, my work includes like applying AI to healthcare stuff. So I chose this data set called list classification. It's available on Kaggle. So the data set is its WBC classification. So it has five subtypes: basophils, eosinophils, lymphocytes, monocytes, and neutrophils. So the task is to classify between these. So the reason I applied heat maps to this is, one, it is related to the data set that we will be using at work, and second, the visualizing heat maps in these kind of data sets is very important because you need to understand how the CNN is classifying different cells. Because if I, as not a domain expert, sees the cells, everything looks same to me, but they are different, and we need to understand how the CNN is actually classifying these different cells for giving accurate results. So it's a pretty small data set, it's around 250 images. So it's good for experimenting stuff. My validation set had only around 25 images, out of which my basic ResNet 34 got all of them right except 2. The interesting part is in the one of them. So this is like the basic batch of the data set, lymphocytes. This is a cell over here. It is a lymphocyte. This is a cell basophil. This is a monocyte. You can see it has some like transparent layer around it. So what I did was I used the interpretation learner from Fastai library and got the top correct and top wrong images, and I applied heat maps on them. So this is like the array of those images. So the one thing I noticed with Fastai library is that these images are rectangular images, and when we do plot top losses using the Fastai library, it does not work with rectangular images. So you can see the heat map over here, it is corresponding to cell, but it is like shifted down for some reason because the Fastai library like swaps the axis for width and height. So it does not work with rectangular images. So I like made my own small function to do the same thing. The interesting thing over here is, so I plotting the correct prediction, so we can see the cell is over here and the CNN is actually looking at over the cell. The interesting thing is in this top incorrect losses, these are the two wrong ones that you can see over here. The confusion matrix, it has only got 2 wrong because the validation set is only like 25 images. Out of that, it got 2 wrong. So the interesting case is this one. You can see the prediction is eosinophil, but it's actually lymphocyte. And we can see why. The cells are over here in the image, but the CNN is actually not looking over there. It's looking at this artifact. So probably we can use this interesting like classification. We can use this interesting result of how the CNN is looking at the image to fix this issue. So this is actually not a cell. It's an artifact. It's probably from the microscope or the slide. So the CNN is thinking that this is a cell, but it's not. So that's why it is an incorrect prediction. It is like 47% probability of being a cell and being an eosinophil.
So it's not really that. I mean, it's not really a bad prediction in the sense that it's not really confident that it's, in other words, if it only believes 47% that if the model only thinks 47% that it's an EOS, whatever that is, then it's not as bad a mistake as it would have been if the model was 90% confident it was that class.
The actual problem is, if you see just number 47%, we can think it's good, but when we plot the heat maps, we can see over here it's not actually looking at the cell, it's looking at the artifact.
It's looking at the wrong thing.
Yeah, so it's 47% that artifact is a cell, which can be a problem because it's not a cell at all. And the other interesting,
what is this model? I'm sorry. What is this model trying to predict? Is it 2 classes? Are there 2 classes, lymphocyte and eosi, whatever?
So these are the 5 classes, WBC subtypes.
Okay.
Yeah.
I see.
Yeah.
I see. Oh, okay. So that's why 47% is not a bad. It is actually high because random would be 20%.
Yeah.
I see.
And another experiment I did was in plotting the heat maps, we take the average around the features. So we get like the region around which the CNN is focusing on. So if we see the image, this is actually a linear interpolated rescale to the original size. So it gets around this region. So I tried one experiment. Instead of like taking the average around the features, I tried to take around the maximum activating features. So we can see that it actually focuses on those eyes to see to do the prediction. So I think like this must have been already done or something. So I just tried to and thought of just sharing this, that by using like the instead of average activations, I take the maximum of the dimension 0. So it actually like focuses on to which part of that region. You can see it only focuses on these 3 major pixels which correspond to like the eyes and the nose.
Jayesh, could you show the previous one where we're using average instead of max? Because I just want to see that comparison. The previous one,
yeah.
the dog one.
Yeah,
I
this
see.
one is,
so there's mostly focused around the snout. There's mostly focused around the snout, and then in the average and the max, it's mostly focused around the eye.
Yeah. In the average, it's focusing mostly on the face. But if we use the max, we can see that it's actually focusing on the eyes part of the face.
Yes. That's really nice.
Yeah, that's it.
Thank you, Josh. That was terrific. Does anyone want to talk about ethics? Because that is the last section of chapter 6. Does anyone have anything to say about that?
I've started this thread on the part 2 category, so please involve yourself there if this topic interests you. The other thing that's sort of a heated discussion right now is Swift for TensorFlow. So I'm not sure if Ramesh is still on the call. He actually attended the Dev Summit in person. So I'd like to hear his thoughts as well on this Swift for TensorFlow picture.
I'm not sure how much time we have left, but Nicholas had a paper or could present a paper, I think, that he shared on Medium, but I think we don't have enough
we have
time.
8 minutes, so maybe we could move it to...
Yeah. You're right. Yeah.
I'd be happy to do a quick overview. I don't think it'd take very long, but we're obviously it's 12.
By all means, yeah.
Go forward, Nicholas.
Yeah, by all means.
Okay, sure. Just go ahead and share my screen. Is that let me see if I can.
Yeah, we see it.
Okay, great. So I wrote this paper, I don't know, maybe 3 weeks ago or so. And it basically was based on some thoughts about a potential explanation for the mechanism behind dropout regularization, which, the thinking goes, oh, there's the soundtrack, but I'm not going to get into that. But the idea is that the paper uses some abstractions and analogy to try to compare the regularization achieved through L1 and L2 regularization and what is being achieved with dropout. And I kind of use a description of dropout demonstrating that there are a subset of models in a fully trained network that are kind of in a kind of non-quantum superposition, and that's kind of what guided my thinking to what's being demonstrated. And this paper is more of a hypothesis than it is really well-tested theory, but I just wanted to document it. About L1 and L2 regularization is a means to draw analogy, and we talked about L1 and L2 regularization in this presentation, so I won't go into a lot of detail. But one of the key things I wanted to demonstrate is that what was being achieved with L1 and L2 regularization is that with L1 regularization, you're shifting the weight set to increase sparsity, such that you have weights that are reduced in an inconsistent manner, such that some are at a higher threshold and some are pushed towards 0. And while in L2 regularization, you're more of a global shift towards reduction in the weight set. And so the disparity in the results of regularization is kind of analogous to what I'm trying to propose for Dropout. So, I give kind of a high-level overview of Dropout. I'd like to put it to a comprehensive summary, but this is just kind of an abstraction. As we all know, what's being demonstrated with Dropout is it uses, probabilistic stochastic reduction of the nodes in the network to form but I guess another abstraction I use to talk about is the idea that in the supervised training of a neural network, we have known inputs and known outputs, and the navigation of the state space of neural network weightings is such that it's kind of evaluating this collection of examples to identify transformation functions, which transform our input, which is our features, into our output, which is our activation for the output of it. So, I give the example, these inputs could be JPEG images, and the output could be a indication of whether the image contains a hot dog. And here, this is an abstraction of polynomial functions to demonstrate the input, the output. And this kind of ties into what I'm going to demonstrate, in that you can see that there's a lot of different ranges of transformation functions that get from the input to the output. And in the collection of examples and labels, we're able to identify transformation functions of similarity. And this isn't literally what's being accomplished with backpropagation, but it's kind of an abstraction to help you think about what's being achieved. And this gets into Dropout, where the whole hypothesis of this paper is that there's scales of linearity in the transformation, and that just like in a polynomial function, where for f of x equals x, a linear function would be such that if you add x1 and x2, it's equal to the sum of f of x1 and f of x2. Whereas on a nonlinear function, that would not be the case. An example is a polynomial function, a g of x equals x squared. That would be not linear, because g of x1 plus g of x2 is not equal to g of x1 plus x2. And this kind of ties into fitted polynomial curves, which is like a simple form of machine learning, and that there's what I'm proposing here is that there's scales of linearity, and that as we apply higher levels of regularization or higher ratios for Dropout, for instance, the linearity demonstrated in our transformation function will trend towards increased linearity. So it'll, this is a high order polynomial, this is a lower order polynomial, and as we apply higher levels of the Dropout regularization, it'll trend in this direction. And that's really, and so I propose a method to evaluate that. And that would be equivalent to, in this slide, regularization would shift us from a high order polynomial to a lower order polynomial. And there's a piecewise linearity, because a curve can be linear in one section and nonlinear in another, but it's a way to estimate the effect. And so I guess the conclusion is just that, analogous to how L1 and L2 regularization shift the weightings in such a fashion that I described, I'm suggesting that Dropout shifts the transformation function, and it shifts it in a manner towards increased linearity, as could be demonstrated by the method proposed. And there, I think I got it in 5 minutes.
Thanks a lot, Nicholas. I think that was very interesting.
Okay, cool. So yeah, and any feedback on the paper is welcome. I'm on Twitter. If you want to see me on Twitter. Oh, and just a quick plug before I drop off. I have some open source software that automates data wrangling for machine learning, and it's available at automunge.com, and you can learn more there. I also recently completed my first collection of essays. It's linked in the pinned tweet on my Twitter handle, which you can find me under my name, Nicholas Teague, or _NICT_. And the book is called From the Diaries of John Henry, and that's I'm trying to get the word out. So it's just a collection of essays, some on machine learning, some on physics, some on just creative writing, and it's been what I've been working on for the last few years. So feel free to share.
Okay, thanks, Nicholas.
Okay, thanks.
So I think we're at the end. And anybody have anything else to bring up before we knock off?
I think if we could have a little starter discussion on Swift for TensorFlow and maybe continue that in Slack. Because I think from our little discussion inside of the chat, many of us like me are getting the wrong idea that Swift will solve this Python situation where Python is slow, which, like Ramesh pointed out, is really not the issue because training happens on the GPU.
Yeah, I can give a few the way I see the world. Everything is opinionated. Okay, so please take mine as opinions. And before that, hey, thanks, Nicholas. That's a great presentation. And I love Houston. I used to live in Houston for a long time. I'm very fond of city.
Cool.
Yeah. So on the Swift itself, I think it's good. I think it's a nice API. It's not at least Java for TensorFlow. Okay, so it is a high-level language. Okay, so it tries to solve many of the problems of these dynamic languages like Python, Ruby, and other languages. Right. So directionally, it's great. Okay, but is it ready to be used this year? Probably not. Okay, is it ready? Will it be ready in 5 years? Most likely, right? So I wouldn't worry about it at all, because if you go to your company and say, I'm going to do Swift with TensorFlow, they say, great. Now, how many companies have it? And you say, none. Okay, it's not even ready. Like there is not even TensorFlow 2.2 doesn't have it. TensorFlow just realized that their API is terrible, and they have standardized on tf.keras. Okay, tf.keras only exists in the Python API. It doesn't exist in Swift API. Okay, so it is a toy example that will work for some very specific use cases, like maybe people that do distributed training crazy with multiple 10,000 node GPUs and have that sort of a problem. Yes, it can be useful, but you will not have pandas. You will not have NumPy. You will not have this beautiful Python ecosystem. Okay, so none of that exists in Swift. Okay, so this is primarily the way again, it's all opinionated. My understanding as to why Julia failed to conquer it. Okay, why lots and lots of other great languages, including Go, failed to conquer this data ecosystem. They are all faster. They are all actually have very expressive languages. Right? They're not Java. Okay, so but they failed to conquer it is because of this ecosystem problem. I think if you look back 10 years ago, Python had the same problem. R was the king of data, right? Because even though nobody liked R, everybody were using R because Hadley Wickham had built so many awesome things with R, and those didn't exist in Python ecosystem until data frame came into Python. Nothing really happened with Python ecosystem. So I think eventually Swift could be that language that we will all end up using in 5 years from now. I think it's quite natural, right? Like, I think I think of languages just like how I think of frameworks, from PyTorch to TensorFlow, or even Fast.ai. These are just tools, right? For my current problem, a set of tools are useful to me. But am I afraid to pick up a new tool, maybe a new power tool, 2 years from now? No, I'm not afraid to make a new power tool 2 years from now. But I cannot go around and say, let me try this self-driving car on the road today. Okay, I have a stick shift. I will drive my stick shift today, and eventually I will get to 10 years from now. Maybe self-driving car is the way to go. So I think you just look at it with curiosity. I think most important thing right now is applying these techniques onto interesting problems. And I think that's Python API is great for us to get there. And I think that's really what I want to focus on and not be too concerned about, you know, I'm not writing a compiler to say, hey, Python is slow, I want Swift or anything else. So trying to remove the clutter. I think I'm a little bit like concerned that Jeremy brought this up before the course started. I think it would have been easier if he held back on the news until week 4 of this course and then started that. Otherwise, people are already getting, thinking ahead and saying, oh, maybe in part 1 of V4, maybe it's in TensorFlow, maybe it's in Swift, who knows, right? But then Jeremy likes to play around with these things, right? He likes to, and that's the beauty of him, just experimenting and doing things. That's what takes him. But I would, what actually concerns me, honestly, is if Jeremy is going to move his personal, space into Swift and TensorFlow, what's the future of Fast.ai as a library, right? Can I rely on it to use it later? So that's what I'm actually more concerned about. So I still don't use Fast.ai in production or anything. I just use it to, it's a toy library that I can use to really get to results quickly and play around with ideas. But I don't use any Fast.ai in my actual work. So anyway,
that's a really valuable perspective, I think, because it really seems like Jeremy is not afraid of the challenge, and he sees that that Swift isn't there yet now, but he's visualizing what can happen 5 or 10 years in the future if he and other people build it out to remedy all of the shortcomings that you mentioned. But in particular, the whole lack of the Python ecosystem, including PyTorch, is a really worrying thing. Like, you can't really, like you said, you can't really start thinking, oh, I'm going to build all my models in Swift now, because the pieces, the infrastructure isn't there yet. And I also agree with you that it's causing me to have doubts about the future of Fast.ai, because I've been thinking of Fast.ai as a library that's going to take over the world. And now if Jeremy's going to throw all his energy into Swift, that's a worrisome thing to me. So.
No, absolutely right. I think again, it may not be 5 years from now. It could be 2 years from now. It could be even be a year from now. Maybe next year's TensorFlow Summit will include a lot more. The way they promoted Keras API this year, they might say now Keras is everywhere. So Keras, you can do the same Keras API in Swift. Okay, this is quite possible. And then people might say, oh, for my problem, I'm going to use TF for Swift and go forward with it. But the way, honestly, I came out of this conference is I'm not too sure if PyTorch is relevant anymore. Okay, and I'm a huge fan of PyTorch. I'm like, I love PyTorch. Okay, but I am not too sure if, unless, I still think PyTorch has the best API, has the most simplest API, does the minimal thing that is necessary, and gets out of your way very quickly. Okay, none of that applies to TensorFlow. None of that applies to Keras. I can't even do a good differential learning rate in TF Keras.
Do you think that's still true with the 2.0 release, or do you think they've addressed?
I still think so. TF.Keras is still not there. Like, it does so many things. Like, this is like Swiss Army knife. It does so many things. But with PyTorch, you can write down the entire API in a sheet of paper, and you know everything you need to do. I'll tell you the biggest problem with TensorFlow. This is the biggest problem with TensorFlow. You go back 3 months back, look at somebody's repo, okay? And I will tell you that way is it's not the way to do it today, okay? and you look at somebody's repo today, and you go to 3 months forward, and you can almost guarantee that this way is not the right way 3 months from now, okay? But you go to PyTorch GitHub repo, any example, year before, in 0.2, the very first release, and you look at it today and say, oh, 90% of the API is still relevant. Maybe you don't need a variable, you just need use tensor. That's all it is. The API has not changed, right? So I think that's a huge asset. Like, even I think that's the biggest benefit. But I'm not too sure, because I think the industry adoption is still somewhat
TensorFlow.
missing. Yeah, I think TensorFlow has had the best marketing campaign in this business. Yeah. Yeah,
Like,
but I think it's good. Yeah.
I sort of try to get freelance work, and wherever I look, I only find TensorFlow relevant jobs. And I think people like Jeremy and Ramesh, who sort of have this industry experience or how to put models into production, might have that long-term view of how Swift might or might not fit into the picture. For us, it's just that we're excited that Jeremy is sort of trying this new thing. So we should be cautious of if we should be investing time there learning Swift or really polishing up on part one. Like, what's our priority right now? That's one thing that I'm taking away from this discussion.
Yeah, definitely get better at deep learning. Don't worry about framework.
Yeah.
Don't worry about Swift. Don't worry about anything. Just get better at deep learning. And today it's PyTorch for us because that's what we want to do for part 2, right? Like, let's not, but I think the great thing is TF Keras is very similar to PyTorch, which is great. Like, I'm glad they copied the API to such a big extent, because now it makes it easy for us to take a project and say, oh, do it in Keras. Like, oh, no big deal. I just know a few API I need to map, and it looks very similar to me. So it's all good. It's all good for us as users of these frameworks. All right, yeah, that's all I had. Go ahead.
Yeah.
Thank you, Ramesh. That was.
Thanks. That was good discussion.
We'll be the beneficiaries at the end, even if the frameworks converge or keep copying from each other.
Yeah, absolutely. Without PyTorch, TensorFlow would not have gone to eager execution, right? And similarly, other vice versa could too, right? Without TensorFlow, PyTorch would not have given a C++ API. So this competition is actually a good thing.
Yeah, I mean, just like Fortran, Fortran is still around, but the reason is that it kept adapting itself first with Pascal and then with to try to make it itself consistent with all of the new developments since the 60s, and it's still around. So yeah, that's what happens with competition. The ideas get shared around, and everything gets better.
I'm sorry, my Zoom app had just crashed.
Okay. I was just saying that, what you said is right. I mean, we're all going to benefit from the competition, because the ideas get shared around, and then every framework sees them and improves itself, and then eventually the best framework will win. True. Or the best few frameworks will win.
Like, at least at some point of time, we'll have to use TensorFlow because that's what everyone uses in the industry. Yeah. Unless we're doing some research or Kaggle competitions, which is where people are okay with using PyTorch.
Yeah. Okay. Well, now I'm a lot less excited about Swift than I was before this meeting. So,
I think this was a much needed discussion.
Yeah. But anyway. All right. Well, I think we can conclude, and thank you everyone, especially for the unexpected contributions that we've had from Ramesh and from Nicholas. And hopefully we'll have an equally exciting meeting next week.
Thanks everyone for joining today.
Okay.